Okay, in this video we're going to begin section 11.3, which is the multiplication rule and conditional probability rule. We'll also talk about something that's called independent events in this section. But definition there, the conditional probability of event A given event B, which is denoted by the probability of A given B is how we read that. Probability of A given B is the probability that A occurs if we know that B has occurred. Okay, so from that we have the multiplication rule, which says that for any two events A and B, the probability of A and B is equal to the probability of A times the probability of B given A. Okay, so let's use that. Problem 30 says, suppose that two cards are randomly selected from a 52 card deck. In part A, what is the probability that the first card is a club and the second card is a club if the sampling is done without replacement? Okay, so once we select a card, we're not going to put that card back. What's the probability that we select two clubs? So for this problem, you're going to have to use the multiplication rule. And the probability of selecting one club would be 13 out of 52. There's 13 clubs in a deck. Once you select the one club, there's now 51 cards left in the deck, and if you've already selected a club, there's 12 clubs left in the deck. Okay, so if you want the next card to be a club, 12 over 51 would be that probability. 13 over 52 reduces to 1/4. 12 over 4 reduces to 3, so I got 3 over 51, which reduces to 1 over 17. So 1 over 17 would be the answer. Okay. Part B, what is the probability that the first card is a club and the second card is a club if the sampling is done with replacement? Okay, so this time the card is going to go back into the deck. Okay, you're going to replace it. The probability that we get two clubs with replacement, well, there's a 13 out of 52 probability that the first card would be a club. Okay, so but that card is going back into the deck. Okay, so when you go to find that next probability, all 52 cards are going to be there and all 13 clubs are going to be there. So you're going to multiply by 13 over 52 again. 13 over 52 is the same as 1/4, so I got 1/4 times 1/4, which is the same as 1/16. And 1/16 would be the answer. Now I've got a note here. Always assume that the sampling is done without replacement if you are not told in the problem. Okay, so never assume that in the problem that the card is going to go back in the deck or the ball is going to go back in the jar or whatever. Okay, unless you're told that. Okay. So just to be clear here, we're using the multiplication rule, which says that you want to take the probability of A times the probability of B given A. So this notation here is the fact that you know something has happened. Okay, so like if I want to find the probability of two clubs, in the second probability, I already know what's happened in the first probability. Okay, so given the fact that I've already selected one club, what is the chances that I select another club? Okay, that's what I'm saying there. Problem 31 says that at a local golf store, they're selling a bag that contains 35 golf balls in it. Suppose that the bag contains 20 Titleists, T, 8 max flies, M, and 7 top flights, F. Okay, part A, what is the probability that two randomly selected golf balls are Titleist? Okay, so for this one, you're gonna use the multiplication rule. By the way, anytime that you got more than one item being selected from the bag or the box or the deck of cards or whatever, it's gonna be a multiplication rule type problem. Anytime you've got one card selected or one item selected from the bag, the box, the deck of cards, whatever, it is not going to be a multiplication rule. Okay, it's going to be just a regular probability, or if the keyword is or, you're going to use an addition rule, or if the keyword is not, it'll be a complement rule. Okay, so you got to pay attention to the keyword there. So in part A, we got to find the probability that 2 randomly selected golf balls are both Titleists. Okay, so there's 20 Titleists in the bag, 35 golf balls total in the bag, so 20 over 35 would be the probability one ball would be a Titleist brand ball. Now I need the next one to be a Titleist brand ball. Okay, so if I've already selected Titleist first, there's now 34 golf balls left in the bag, and 19 of those would be Titleist brand. Okay, so I got to multiply by 19 over 34 if I want the next ball to be a Titleist. 20 over 35 times 19 over 34 gives me roughly 0.319 as the answer. Okay. Part B, what is the probability that the first ball selected is a Titleist and the second is a max fly? Okay, so in that order, the first ball selected is a Titleist brand ball. Well, there's 20 Titleists in the bag, 35 golf balls total in the bag, so 20 over 35 times the second is a max fly. Well, there's 34 golf balls left in the bag if you've already selected a Titleist brand ball. There's 34 left in the bag. All the max flies are still there though, right? So I'm going to multiply by 8 over 34. 20 over 35 times 8 over 34 gives me roughly 0.314, or 0.134, sorry. Okay. Part C, what is the probability that the first ball selected is a max fly and the second is a Titleist? Okay, in that order. A max fly first and then a Titleist second. Well, 8 over 35 would be the probability of selecting a max fly. And once you've selected a max fly, there's now 34 golf balls left in the bag. All the Titleist brands are still there though, all 20 of them. So I'd multiply by 20 over 34. Now if I compare this calculation to the one right above it, all I've done is I've switched the numerators. Okay, so the answer is going to be the same, roughly 0.134. Part D, what is the probability that one is a Titleist and the other is a max fly? Okay, now what they're saying in Part D is different from what they're saying in Part B, because in Part B there was an order set. Okay, and they're not saying anything like that in Part D, just, hey, one's a Titleist and the other's a max fly. Okay, so it can go, you could select a Titleist first, then a max fly second, or a max fly first, and then a Titleist second. Now, or is a key word. Okay, or means add. So I'm going to have to add these two probabilities together. And let's see, I've already computed these probabilities here. So the first one was the answer to Part B. The second one was the answer to Part C. So all I need to do here in Part D is I need to add these two together. 0.134 times plus 0.134 gives me 0.268, which should be the answer. Okay, so in a problem like this, we need to recognize that we've got an addition rule, although they're not using the word or. Okay, that's something that we need to think about on our own, and then use that. Okay. Problem 32 says that due to a manufacturing error, 3 cans of regular soda, capital R, were accidentally filled with diet soda, capital D, and placed into a 12-pack. Suppose that 2 cans are randomly selected from the 12-pack. In Part A, determine the probability that both contain diet soda. Okay, so the probability of 2 diets. Well, the probability of 1 diet is 3 cans of regular soda were accidentally filled with diet soda. Okay, so there's 3 out of 12 will be the probability of 1 diet. And you've already selected a diet from the 12 pack, so there's 11 cans left in the pack. 2 of them would be diets still. Okay, so I multiply by 2 over 11. 6 divided by 12 is 1/2. 1/2 times 1 over 11 would be 1 over 22. Okay, which would be roughly 0.045 if you're using decimals. Part B, determine the probability that both contain regular soda. Okay, well if 3 of the cans in the 12-pack are diet soda accidentally filled, then the other 9 correctly filled are regular soda. Okay, so 9 over 12 will be the probability that the first can will be regular soda. Once you've selected a regular soda from the 12 pack, 11 cans are left in the 12 pack. 8 of them are still regular soda though. Okay, so I'd multiply by 8 over 11. And when I simplify this, so 9 over 12 gives me 3/4. 8 over 4 is 2, so 3 times 2 is 6. 11 would still be in the denominator. 6 over 11 is 0.545. So would that be unusual to select 2 regular sodas? No, that wouldn't be unusual. I mean, you bought a pack of regular soda. There was just a manufacturing error that you did not know about. Okay, but you know, of course, that would be unusual if this were a very high probability or very low probability. Okay. Determine the probability that exactly one is diet and the other is regular. Okay, so, for that to happen, I could select a diet first and then a regular second, or I could select a regular first and then diet second. Okay, either one of these two orders here means that exactly one is diet and the other is regular. Okay, so or is a key word, or means add. And so I got the probability of selecting a diet first and the regular second, plus the probability of selecting a regular first and then diet second. A diet first, okay, there's 3 over 12 is the probability that one can is a diet, and then a regular second, so 11 cans are left in the 12 pack. All the regulars are still there though, all 9 of them. Okay, so I multiply by 9 over 11. Plus a regular first and then a diet second. Okay, so 9 over 12 would be the probability of getting a regular. And there's 11 cans left in the 12 pack. All the diets are still there. Okay, all 3 of them. So I'd multiply by 3 over 11. If I simplify this, 9 divided by, well, let me do this. 3 divided by 12 is 1/4. 1/4 times 9 over 11 would be 9 over 44. All I've done here on the other one is I've switched the numerators there, so I'm going to have another 9 over 44. 9 over 44 plus 9 over 44. Okay, I keep the denominator, add the numerators. That'd be 18 over 44, or 9 over 22 would be the answer to that one. Okay. And by the way, another way to do this, and I'm not sure it'd be any faster or anything, but another way to do this one would be to use the complement rule. Okay, if you need exactly one to be a diet and the other to be a regular, then they're not both going to be diet and they're not both going to be regular. Okay, so if I add these two probabilities together and then I subtract from 1, I should get the same answer, 9 over 22. Just another way to do the problem. Okay. One term that we'll need to know in this section is the term independent events. And it says that 2 events A and B are independent if the occurrence of event A in a probability experiment does not affect the probability of event B. 2 events A and B are dependent if the occurrence of event A in a probability experiment does affect the probability of event B. Okay. As a note, and this will be for later, to define independence using conditional probabilities, you write that events A and B are independent if the probability of A given B is equal to the probability of A, or the probability of B given A is equal to the probability of B. So just because you're given event B, that has no effect. Okay, you can find the probability of A and still get the same result. Or just because you're given event A, so what? Okay, if you find the probability of just B, you end up getting the result of B given A. Okay, so it's kind of like this. You know, what if you're at your desk and you got a deck of cards in front of you, and I ask you, what's the probability of selecting an ace? Okay, and I also tell you that it's raining outside. Well, me telling you that it's raining outside has nothing to do with selecting an ace from the deck, right? So that would be an example of where you have independent events going on. Let's take a look at problem 33. Or problem 33 and 34. Determine whether the events A and B are independent or dependent. 33, part A, event A, you earn $50,000 in a year. In part B, you are born in December. Okay. So are these events independent or dependent? Well, they're going to be independent since the occurrence of one does not directly affect the other one. In other words, just because you make $50,000 in a year, that has nothing to do with the month that you were born in, right? And vice versa, if you're born in December, that has nothing to do with the amount of money that you make in a given year. Okay, so those would be independent events. Problem 34, event A is the event that you earn an A on the next statistics test. In part B, you study for the next statistics test. Okay, that would be an example of dependent events, since one could directly affect the other one. Okay, if you get an A on the next test, maybe it's because you studied for the next test. Or vice versa, if you study for the next test, it could have a direct effect over what letter grade you end up getting on the next test. Okay. There's a caution statement here which is very important. It says that independent events are different from mutually exclusive events. That is very important. Okay, make sure that you know that. Problem 35, draw a Venn diagram for problem 33. This illustration will be an example of the caution statement given above. Okay, so in problem 33, I got, here's the sample space, and the number of people that make $50,000 in a year and the number of people that are born in December. Okay, now there are people in the world that are born in December and make $50,000 in a year. Okay, so those people would be in the overlap. Okay, now are these events mutually exclusive? Okay, no, they're not mutually exclusive because there's an overlap, right? There are people in the world that are born in December and make $50,000 in a year. Okay, so because those people exist, that would mean that this is not mutually exclusive. Okay, they're independent events. We've already said that. Okay, but they're not mutually exclusive. So independence is different from mutually exclusive. Okay, as a note, two events are mutually exclusive means that they're also dependent. Okay, and when we look at that, well, we'll look at that now. Draw a Venn diagram to show the possibilities of July 4th, 2030. This illustration will be an example of the note given above. Okay, so July 4th, 2030 is going to fall on one of these 7 days. Okay, I don't want those to overlap. Okay, because days don't overlap. Okay, so clearly, I'm going to have mutually exclusive events, right? Because the days don't overlap. Okay, so now why is this dependent? Well, it's going to be dependent if July 4th, 2030 is on a Monday, then that will affect the other 6 days. Okay, so that has a direct effect over July 4th falling on Thursday or Friday or something like that. It's not going to land on any of those days. Okay, if it lands on Monday. Okay, so it depends on which day it falls on. Okay, and that'd be an example of the difference between the two there. So, okay, why don't we go ahead and stop right here in the notes, and we'll pick up with problem 37 in the next video.